Hello everyone. In today's video, we will talk about functions. We admit that the student already know to deal with limits and derivatives. So we can in this video work with the study of functions and their properties. So let's start. First, asymptote to a curve. Consider a function f and designate by c its representative curve in an orthonormal system OIJ. If limit of f of x as x tends to a, where a is a real number, equals to plus or minus infinity, then we can say that the straight line d of equation x equals to a is a vertical asymptote to the curve c. Here we have the curve c, and here's the vertical asymptote with the equation x equals to a. Now, if limit as x tends to plus or minus infinity, so the function f of x equals to b, where b is a real number, then we can say that the straight line d of equation y equals to b is a horizontal asymptote to c. Here's the curve c, and this is the horizontal asymptote to c of equation y equals to b. If limit as x tends to plus or minus infinity of f of x minus this term ax plus b equals to 0, then we can say that the straight line d1 of equation y equals to ax plus b is an oblique asymptote to the curve c. So here's the curve c, and here's the oblique asymptote to the curve c. 2. Continuity of a function at a point. Let f be a function defined over an interval I. Then we say that f is continuous at the point a, where a belongs to I, if limit as x tends to a of f of x equals to f of a. If we say that f is continuous over the interval I, if f is continuous at every point of I. F is said to be discontinuous at the point a if it is not continuous at a. Here's the graphical interpretation of the continuity of a function. If f is continuous over an interval I, so its representative curve c can be drawn as continuous curve without any breaks, holes, or jumps or vertical asymptotes. So here in the following figure, c is a curve representing a continuous function. Here, c is a curve representing a discontinuous function at this point, because here we have a jump. Differentiability of a function at a point. Let f be a function defined over an interval I, and c is its curve. We say that f is differentiable at a point a of I if this limit exists. This limit L is equal to limit as x tends to a of f of x minus f of a over x minus a, or equivalently, L equals to limit as h tends to 0 of f of a plus h minus f of a all over h, where h is x minus a. So this limit has to be exist. So it will be a real number and unique. Remark, if f is differentiable at a, then f prime of a is L. So L, it will be the derivative of f at the point a. And there exists only one tangent t to the curve c at the point with abscissa x equal a. Because L is unique, so f prime is unique, and f prime is the slope of the tangent. So we conclude that we have a unique tangent to the curve c at the point with abscissa a. Now, let's find the equation of this tangent. So if f is differentiable at the point a with coordinates small a and f of small a, then as we know, c admits a unique tangent t at capital A. The equation of this tangent is y minus f of a equals to the slope, which is f prime of a multiplied by x minus a. Derivative of a function. These are recalls for you. Let f be a differentiable function over the interval I, so the derivative exists and denoted by f prime of x. Here, for every function, we put its derivative. The derivative of a constant is 0. The derivative of ax equals to a. The derivative of ax power n, this is the power rule, is a multiplied by the power n multiplied by x to the power n minus 1. We subtract 1 from the power. Derivative of 1 over x is minus 1 over x squared. Derivative of square root of x equals to 1 over 2 square root of x. Derivative of u power n, this is like the power rule, but here we multiply by the derivative of u, because u is a function of x, not the variable, but function of x. So derivative of u power n is n u power n minus 1 multiplied by u prime. Derivative of square root of u is u prime over 2 square root of u. The derivative of the sum or the subtraction of u and v is u prime plus or minus v prime. Derivative of product is u prime v plus v prime u. Derivative of constant over u is minus constant times u prime over u square. Derivative of the quotient u over v is equal to u prime v minus v prime u over v square. This is an important formula in the functions, in the study of the functions. Derivative of cosine x is minus sine x. Derivative of sine x is cosine x. Derivative of tangent x is 1 plus tangent square x, or 1 over cosine square x. Derivative of cosine u, where u is a function of x, equals to minus u prime times sine u. And finally, derivative of sine u is u prime multiplied by cosine u. Now, the parity of a function. The parity of a function, meaning that if a function is even or odd. Let f be a function defined over an interval I, which is a subset of R, or its R, and let C be its representative curve in an orthonormal system OIJ. F is said to be an even function if we have these two conditions. The domain of f is centered at 0, or for every x belongs to I, we have minus x belongs to I. For example, the domain R is centered at 0. The domain minus 2 is centered at 0. We must have O is the midpoint of the interval. The domain minus 3 is centered at 0. The second condition must we have f of minus x equals to f of x. For example, the parabola, the standard parabola f of x equals to x squared is an even function because its domain is minus infinity to plus infinity, centered at 0. Moreover, f of minus x equals to minus x all squared equal to x squared, which is equal to f of x. So here f of minus x equals to f of x. So f of x equals to x squared, the standard parabola, is an even function. In the case of even function, the y-axis, axis of ordinates, is the axis of symmetry. For the odd functions, similarly, we have two conditions. First condition, the same as even function. We have to find if x belongs to I, then minus x belongs to I, or the domain is centered at 0. Moreover, f of minus x must be minus f of x and not f of x. In the case of the odd function, the origin O00 is the center of symmetry. We have here axis of symmetry as y-axis. In the odd case, we have origin O center of symmetry. For example, the function f of x equals to x cubed is an odd function because f of minus x equals to minus x all cubed, which is equals to minus times x cubed equals to minus f of x. So here we have the two conditions are satisfied. So the function f of x equals to x cubed is an odd function. Center of symmetry of a curve. Here we have a function f and see its representative curve. The point I has coordinates small a and small b. To prove that I of coordinates AB is the center of symmetry of the curve, we have to prove one of these two conditions. Even f of 2a minus x plus f of x equals 2b, or f of a minus x plus f of a plus x equals to 2b. If one of these conditions is proved, then we can say that the point I with coordinates a, b is the center of symmetry of the curve C. For the axis of symmetry, to prove that the straight line D of equation x equals to a is an axis of symmetry for the curve C of f, we have to prove also one of these conditions. Even f of 2a minus x equals to f of x, or f of a minus x equals to f of a plus x. Now for the sense of variation of a function. We have to study the sense of variations of a function. This idea is the most important idea in the study of functions. Let f be a differentiable function so that the derivative of the function exists over an interval I, which is subset of R, and let f prime be its derivative. So we have to know that if the derivative is positive, then the curve of f will be increasing. So here the curve of f is increasing, so the derivative is positive. If for every x belongs to I, if the derivative is negative, then f will be decreasing. Here in this part, the derivative is negative because this part is decreasing. Also here, f of x, f prime of x negative, and the function is decreasing. And if for every x belongs to I, here for every x belongs to I, not 1 point, if the derivative is equals to 0, then f is a constant function over this interval R. Remark, here we have, if the part of a function is above the x-axis, then the function here is positive. If the part of a function is below the x-axis, then we have f of x negative. And when the curve C of the function f cuts the x-axis, we have f of x equals to 0. These are very important for graphical solutions. Extremum of a function. So for every curve or for some curve, we may have a maximum point and a minimum point. We have to find them. Let f be a function defined and differentiable over an interval I, and denote by f prime its derivative. Let a be a point of I. Here, if the derivative at the point A is 0, so we will have an extremum, even a maximum or a minimum. If it is 0 while it's changing the sign at A, then we call it a local maximum. But if it changes from negative to positive, then the function will be local minimum for here, from negative to positive, from decreasing to increasing, vice versa for the local maximum. So at the maximum point, here we have at A, and at the minimum point at B, the derivatives are 0. So f prime here at A is 0, and f prime here at B is 0. Here we have the maximum, here we have the minimum. So the maximum is f of A, and the minimum is f of B. The maximum is at A, and the minimum is at B. Now for the graphical solutions of the parametric equations f of x equals to m. How to solve this equation? Here f of x equals to m. So as we see here, f of x equals to y equals to m. So we can draw these horizontal straight lines. And we will count the number of intersection points of the line and the curve. So if the line cuts the curve at 2 points, so the equation f of x equals to m admits 2 distinct roots. Here we have one unique root, and here we have no roots because the straight line and the curve does not meet. Now let us solve the following exercise. This is a very important exercise because it contains all the ideas we mentioned above. So consider the function f defined over minus infinity 3 union 3 to plus infinity opened by f of x equals to x squared minus 5x plus 7 all over x minus 3 and see its representative curve in an orthonormal system OIJ. Here the domain is like that because x minus 3 does not equals to 0, so x does not equals to 3. So we have an open interval at 3. We have to find the limits of the boundaries at the boundaries of the domain of definition of f. So here we have 4 limits at minus infinity, at 3 here, and at plus infinity. Here at 3 minus and here at 3 plus. Then we have to find the derivative and we will study its sign. We have to set up the table of variations of f. We have to find the oblique asymptote. We have to find the center of symmetry, writing equation of tangent. We will trace the curve and the asymptotes, and then we will study a graphical solution for this equation f of x equals to m. So let's start. We will start with the limits. So as we mentioned before, we have 4 limits. Let's start with the limit at minus infinity. Limit as x tends to minus infinity to f of x equals to, here we have f x, x squared minus 5x plus 7 over x minus 3. So we will have here plus infinity over minus infinity, which is an indeterminate form. So we will take out this highest power here, which is x squared, and the highest power from the denominator, which is x. So this limit equals to limit as x tends to minus infinity of x squared over x, which is x. So limit as x tends to minus infinity of x equals to minus infinity. Similarly, the limit of f of x as x tends to plus infinity will be plus infinity, because if we substitute plus infinity instead of x, we will have this limit equals to plus infinity. Now the limit as x tends to 3 but minus before 3 here. So we will put here 3. 3 squared minus 5 multiplied by 3, 15 plus 7 over 3 minus 3. Here's 1 and 3 minus 3 is equals to 0 minus. We know that constant over 0 is infinity. And here we have positive over negative, which is negative. So the limit as x tends to 3 minus of f of x equals to minus infinity. Similarly for the fourth limit, but here we will have 3 plus minus 3, which is 0 plus. So 1 over 0 plus will be plus infinity. Remark, here we have limit as x tends to 3 of f of x equals to infinity. So we can conclude that the straight line with equation x equals 3 is a vertical asymptote. Now for the derivative, finding f prime. Here the form of f is equal to a quotient u over v. So we will use this formula. Derivative of u over v is u prime v minus v prime u all over v squared. So derivative of u over v is u prime derivative of u multiplied by v. Derivative of u here is 2x minus 5 multiplied by v minus v prime derivative of x minus 3 is 1 multiplied by u, which is x squared minus 5x plus 7 all over v squared, which is x minus 3 all squared. Here we will perform the expansion and then simplify to get x squared minus 6x plus 8 all over x minus 3 all squared. We can factorize this term using the quadratic formula or using the calculator. So we will have f prime of x equals to x minus 3 into x minus 4 all over x minus 3 all squared. So now we have to find the sign of f prime of x, or to study the sign of f prime of x. Here we have a quantity square. So we will study the sign of x minus 2 and x minus 4. As we know, the sign of the product of two binomials is same, opposite, same. Same as the product of these two signs, plus. So here we have between 2 and 4 minus, because the rule is a plus minus a plus. So before 2, for x less than 2, and after 4, the derivative is negative, positive, and between them, the derivative is negative. Now, we will build the table of variations of f. We put x, f prime of x, and f of x. Then we put here the domain from minus infinity till plus infinity, but we have 3 is not included in the domain, so we will put a dashed bar. Then we will put the numbers that vanishes the derivative, which is 2, which are 2 and 4. So here we have 2 and 4. We put here zeros because 2 and 4 vanishes f prime of x, or f prime of 2 equals to f prime of 4 equals to 0. Here we put the sign of the derivative. As we know, before 2 and after 4, the derivative was positive. Between 2 and 4, the derivative was negative. So here, derivative is positive, so f is increasing. We put an increasing arrow. Here, f is decreasing because derivative is negative, and here derivative is positive, so f is increasing. We put the limits. We know that the limit as minus infinity is minus infinity. The limit at 3 minus is minus infinity. The limit at 3 plus is plus infinity. And the limit at plus infinity is plus infinity. Here we put f of 2. So in the expression of f, we put 2. So f of 2 is 2 squared minus 5 multiplied by 2 plus 7 all over 2 minus 3, which is minus 1. And here we put f of 4. After calculation, we have 3. So f of 4 equals 3. A small remark, here we have at 2 a maximum. So the derivative at 2 is 0. And here we have the derivative at 4 is 0, and we have a minimum. So at extreme points, the derivative vanishes. Now, we have to find the real numbers a, b, and c, so that f can be written under the form ax plus b plus c all over x minus 3. So fx equals to ax plus b plus c all over x minus 3. Here we have ax plus b multiplied by x minus 3, and here we have a plus c all over x minus 3. We make a common denominator. So here we will expand, and then after simplification, we get fx equals to ax squared by grouping the terms minus into 3a minus b multiplied by x plus c minus 3b over x minus 3. But we know that f of x equals to x squared minus 5x plus 7 all over x minus 3. By comparing these two formulas or these two expressions, we can say that the coefficient of x squared here, which is a, is equal to the coefficient of x squared here, which is 1. So a equals to 1. The coefficient of x here is equal to the coefficient of x here. So 3a minus b equals to 5. And the constant here is equal to the constant here, which is c minus 3b equals to 7. We get a system of 3 equations with 3 unknowns. By solving this system, we will get a equals to 1, b equals to minus 2, and c equals to 1. So here we will put a equals 1, we will substitute b equals minus 2, and c equals 1. Therefore, f of x equals to x minus 2 plus 1 over x minus 3. Now we have to show that this straight line D with equation y equal x minus 2 is an oblique asymptote to the curve C. So we will apply the formula limit as x tends to plus minus infinity of f of x minus the y of the straight line, and it must be 0. So here fx is equal to x minus 2 plus 1 over x minus 3. We will take this expression because it's more easier. Minus y of t minus into x minus 2, which is minus x plus 2. we can cancel out x minus x and 2 minus 2. We will get the limit of 1 over x minus 3, which is 1 over infinity minus 3, and 1 over infinity equals to 0. This limit equals to 0, so we will conclude that y equal x minus 2, this straight line with this equation, is an oblique asymptote to the curve C. Now we have to study the relative positions of C and D. So we will subtract them and study the sign of their subtraction. So f of x minus y equals to 1 over x minus 3. We know that if x less than 3, this expression will be negative. So the curve C will be below the straight line D. And this expression is positive for x greater than 3. So for x greater than 3, the curve C will be above the straight line D. Now part 6, we have to show that the point I with coordinates 3, 1 is a center of symmetry of C. Here, small a equals to 3 and small b equals to 1. Now we will apply the formula. We have to show that f of 2a minus x plus f of x equals 2b. F of 2a minus x, which is f of 2 multiplied by 3 minus x, which is f of 6 minus x. So in the expression of f here, we put instead of x 6 minus x. So f of 6 minus x equals to 6 minus x all squared minus 5 into 6 minus x plus 7 all over 6 minus x minus 3. Now after expanding this and then simplify, we will get f of 6 minus x equals to x squared minus 7x plus 13 all over minus x plus 3. Here we can multiply by the negative sign above and below to get f of 6 minus x equals to this expression. Now we will add up f of 6 minus x plus f of x. So this expression plus this expression, and then we will have 2x minus 6 over x minus 3. Taking 2 common, we will get the following form. Then we can cancel out x minus 3 and x minus 3, which is equal to 2, which is equal to 2 times 1 equals to 2b. We get f of 2a minus x plus f of x equals to 2b. Therefore, we conclude that the point with coordinates 3, 1 is the center of symmetry for the curve C. Now we have to write the equation of the tangent to the curve C at the point with abscissa 1. So we will apply this formula. The equation of the tangent T to the curve C at the point of abscissa 1 equals to y minus f of 1 equals to f prime of 1 multiplied by x minus 1. Then we have to find f of 1. So f of 1 equals to 1 squared minus 5 multiplied by 1 plus 7 all over 1 minus 3. So by calculating f of 1, we get minus 3 over 2. Here f prime of 1, we will not derive f of 1. We take this expression. We have f prime of x equals to x minus 1, x minus 4 over x minus 3 squared. So in the expression of f prime, we substitute for x equals to 1 to get 3 over 4. So tangent y minus f of a equals to f prime of a, this multiplied by x minus 1. So after simplification, we get the equation of the tangent t, y equals to 3 over 4x minus 9 over 4. Now we have to trace the curve C and D. So according to the table of variation, we will trace the curve C at this graph. So we will first draw the asymptotes. We have x equal 3. We will draw it as dashed line, the vertical asymptote. And the oblique asymptote is of equation y equal x minus 2. We have to start with minus infinity, and up to the point 2, minus 1. So we will start from here, minus infinity at x and minus infinity at y, and then we will start up to the point 2 minus 1. Then after this point, we will start decreasing to minus infinity before 3. So we will decrease up till minus infinity here before 3. Then we have here after 3, we will start at plus infinity and down to the point of coordinates for 3. So after 3, we will begin at plus infinity and go down to the point of coordinates for 3. And then we will go up at infinity. So here we are going up at infinity. For the last part, study according to the real parameter m, the existence and the number of roots of the equation x squared minus m plus 5 into x plus 7 plus 3m equals to 0. Here, first step, we have to write the equation in the form f of x equals to m. So x squared minus etc. equals to 0. Here we will expand this to terms to get this form, and then we will put the m terms before after the equal sign. So x squared minus 5x plus 7 equals to mx minus 3m. Then we will take m as a common factor to get the following result. So m will be x squared minus 5x plus 7 all over x minus 3. This is the equation of f of x. So we will have f of x equals to m. So we will use the curve C of f to solve this equation or to find the number of roots. So here we have, if m is below this number minus 1, a horizontal straight line of equation y equal m will cut the curve C at 2 distinct points. So we will deduce that for m smaller than minus 1, there are only 2 distinct roots. Here at minus 1, we have only one root, which is 2. And between minus 1 and 3, we have no points of intersection between any horizontal straight line and the curve. So we have no roots for m between minus 1 and 3. Here, if m equals to 3, we have one point of intersection with the curve at 4. So for m equals to 3, there is a unique root, which is x equals to 4. And here after 3, or for m greater than 3, we will cut the curve at 2 distinct points. So for m greater than 3, there are 2 distinct roots. This is all for now. Thank you for watching.